In this video, we'll cover the stereochemistry of the Diels Alder reaction. So I'm actually going to scroll up to when we first talked about the Diels Alder reaction, all the way to Diels Alder video 1, and that first reaction scheme. And you may notice that in the product, I drew out now wedges and dashes on the two carbons that were part of the dienophile that are now a part of the ring. When we do the Diels Alder reaction, some of the carbons that are originally sp2 carbons, so just like these two carbons in the dienophile, they become sp3 carbons, which means if they have 4 different groups bonded to them, we now have stereocenters, or R or S stereochemistry. We can say, since we're working with a ring, that the R groups here are cis to each other. There are a few different ways we can describe the product. Another group of carbons that starts as sp2 and ends as sp3 are carbons 4, can't really see that, but carbons 1 and 4 in the diene. In this example, they're bonded each to 2 hydrogen groups, so they don't form stereocenters, but if there were 2 different groups bonded to those carbons originally, then you would end with stereocenters. So let's look at some examples. Scroll back down to our new notes. And let's do a Diels Alder reaction where we have 2-methyl-1,3-butadiene as our diene. And then our dienophile will have 2 nitrile groups. Each one on a different carbon. The product that's formed when these 2 reactants react with each other is a 6-membered ring, which is what we expect. We have a new double bond between carbons 2 and 3 on the diene. And then we have the 2 hydrogens on the carbons that are originally part of the dienophile as both on wedges, and the nitrile groups on dashes. Another product is observed where essentially the wedges and dashes are flipped. So we have 2 different products. These are enantiomers of each other. 2 of the carbons now have stereocenters, which we can describe as R or S. There and over here. One of the key features of these products now is that the groups that are on the same side of the double bond in the dienophile, so the 2 CN groups are the way we've drawn the double bond. They're on the right side of the double bond in the dienophile. Or we can say this is a Z alkene, where the higher priority groups are on the same side of the double bond for the dienophile. So that means the nitrile groups in the products are on the same type of bond. So they're both on the dash in the first example. They're both on the wedge in the second example. The same thing is true for the hydrogens. They're on the same side of the double bond in the dienophile, and they're both on wedges in a product or both on dashes in a product. You will not observe a product where you have one of the green hydrogens on a wedge and one of the green hydrogens on a dash. That product is not possible with these reagents. So let's write that out. Substituents on the same side of the double bond in the dienophile will be on the same side of the ring. In the product, so that means both wedges or both dashes. So here we have the cis alkene so we have those groups cis to each other in the products. Just to show the other possibility for very similar reagents, we'll keep the diene the same, but for the dienophile, we'll have the nitrile group on one side for, we'll say, the top carbon. I'll highlight that one in purple. And the nitrile group on the other side for the bottom carbon, which I'll go ahead and highlight in blue. Then the rest will be hydrogen, bonds to hydrogen. So in the product, we again form the 6-membered ring. We have the pi bond between carbons 2 and 3 from the diene, and then carbon on the top and carbon on the bottom of the dienophile now have new stereocenters. If we put the hydrogen for the carbon on the top on a wedge bond, then for the carbon on the bottom, the nitrile group also has to be on a wedge bond because those two are on the same side of the double bond. And then our wedge for the top carbon is the nitrile group. I'm sorry, the dash for top carbon is the nitrile group. The dash for our bottom carbon is the hydrogen. Because these two, again, are on the same side of the double bond. If this forms, the enantiomer also forms, and that's just when we're switching the wedges and dashes for both stereocenters. So if we now put the nitrile group on the wedge up here, then the hydrogen is on the wedge down there. As long as you can produce one of the products, then you can always get the enantiomer by switching the wedges and dashes. We have a similar pattern for the dienes. If carbon 1 or carbon 4 has different groups bonded to it. So we'll just do a generic example here. We have a diene, we'll say we have 2 R groups. We'll say R naught and R prime for each carbon. And if we just add this to the simplest dienophile, we again get our 6-membered ring with a double bond between carbons 2 and 3. And our new bonds to the diene, new bonds to the dienophile are part of the 6-membered ring. And now, for carbons 1 and 4, we'll say R naught and R prime are 2 different groups. And we say that the 2 R prime groups are on the same side for those 2 dienes. So those will say they're either both on a wedge or both on a dash. I'll draw it on the wedge first. So here's the R prime groups. And then the R naught groups are on the same side. So those are either both on a dash or both on a wedge, and I've drawn them here as both on the wedge. And then the enantiomer, of course, is also another possible product where all you're doing once you find the original, or once you find one of the products, you can produce the enantiomer by switching the wedges and dashes. So now R prime is on a dash and R naught is on a wedge.